Hello there, and welcome. I'm so glad you found your way here tonight. Maybe you're winding down after a long day, or perhaps you're someone who finds comfort in the vastness of space and knowing how small our worries are compared to the infinite cosmos. Either way, this journey is for you. You've got nothing to do but rest. Let your muscles relax, your breathing deepen, and your mind drift freely. Because tonight, we're not exploring the violent explosions or chaotic collisions of space. Instead, we're seeking out the most peaceful corners of the cosmos, the quiet places where time moves slowly and stillness reigns. Before we begin, if you enjoy these calming journeys through space, a like or subscription would mean the world to me. And I'm always curious, where are you right now, and what time is it there? Let me know in the comments. This video is designed to help you fall asleep peacefully. My voice will guide you to the calmest regions of the universe. And then, once our journey ends, authentic space sounds will play for the rest of the night. So settle in. Close your eyes if you wish. Let go of the day's tension and allow yourself to drift with me to the most serene places in existence. When you look up at the night sky, you might think of the cosmos as a place of constant chaos and explosive energy. Stars are born in violent bursts. Black holes tear apart everything that comes near them, and galaxies collide in slow-motion disasters that last millions of years. Supernovae light up the darkness with the brightness of billions of suns. Quasars pour out more energy in a second than our sun will produce in its entire lifetime, and neutron stars spin hundreds of times per second while emitting beams of radiation that sweep across space like cosmic lighthouses. But there's another side to the universe, one that most people never think about, one that doesn't make it into dramatic documentaries or spectacular photographs. Hidden between the bright lights and dramatic events are places of profound stillness, regions so peaceful that nothing disturbs them for billions of years. These are the quiet corners of existence, where time moves differently and silence reigns supreme. To understand the true nature of the cosmos we inhabit, we must look beyond the spectacular and discover the beauty in emptiness, the grace in stillness, and the profound peace that fills most of the universe. This requires a shift in perspective, a willingness to value absence as much as presence, to see significance in what isn't there as much as in what is. We are creatures drawn to activity and drama, evolved to notice movement and change because these things might represent threats or opportunities. Our brains are wired to filter out the constant and unchanging, to focus on the novel and the dynamic. But the universe itself has no such bias. It creates active regions and quiet regions with equal facility. And if anything, it seems to prefer the quiet, dedicating the vast majority of its volume to regions where nothing dramatic ever happens. The universe is far larger than most of us can truly comprehend, and most of it is empty. Not empty in the way a room becomes empty when you remove the furniture, but empty in a way that defies imagination and challenges our intuitive understanding of what space means. Between the galaxies, between the stars, and even between the planets, there are vast oceans of nothingness where you could travel for lifetimes without encountering a single atom. These spaces are not just empty of matter in the physical sense. They're empty of light, empty of sound, empty of change, empty of events, empty of anything that would mark the passage of time or distinguish one moment from another. If you could somehow exist in one of these places, equipped with senses capable of perceiving your environment, You would float in absolute darkness, with no up or down, no sense of motion, and no way to tell if time was even passing at all. The human mind struggles to grasp such emptiness because we've evolved in a world filled with sensory information, where something is always happening, always changing, always demanding our attention. Even in the quietest moments we can experience on Earth, in the deepest caves or the most remote deserts, we are surrounded by air, by rock, by the pull of Earth's gravity, by the faint glow of our own body heat. We breathe, our hearts beat, air currents move around us, and we are constantly receiving sensory input that reminds us we exist in a physical world. But in the deep voids of space, none of these familiar anchors would exist. There would be no air to breathe or to carry sound, no surface to stand on, no horizon to orient yourself by, no background hum of earthly existence to confirm that you are somewhere rather than nowhere. Imagine, if you can, floating in one of these regions. The darkness around you is not the darkness of night on Earth, where your eyes might adjust and begin to see faint details. This is a darkness so complete that adjustment is impossible because there is nothing to see. No matter how long you waited, no matter how sensitive your eyes became, the view would remain the same, an absolute and featureless black extending infinitely in all directions. You might wave your hand in front of your face, and even if you could somehow survive in this environment, you would see nothing. The hand would be there, occupying space, made of atoms and molecules just as it always is, but without light to bounce off it and reveal its presence, it would be as invisible as if it didn't exist at all. The temperature in these regions hovers just barely above absolute zero, the coldest possible temperature in existence, the point at which all thermal motion ceases and atoms become as still as quantum mechanics allows. At absolute zero, which is around minus 273 degrees Celsius, atoms would theoretically stop moving entirely, though quantum uncertainty prevents this from ever quite happening. In the emptiest regions of space, the temperature is typically just a few degrees above this ultimate cold, warmed slightly by the cosmic microwave background radiation that fills all of space, the afterglow of the Big Bang itself. This faint radiation, cooled by billions of years of cosmic expansion, provides just enough energy to keep the universe from reaching absolute zero, but only just. The difference is so small that, for all practical purposes, these regions represent the coldest naturally occurring environments in the cosmos. In such cold, the few atoms that do exist move with almost no energy. A hydrogen atom in one of these regions might drift along at speeds of only a few meters per second, barely moving at all compared to the frenetic thermal motion of atoms in warmer environments. At room temperature on Earth, air molecules zip around at speeds of hundreds of meters per second, constantly colliding with each other and with surfaces, creating the pressure and temperature we perceive. But in the cold of intergalactic space, atoms move so slowly that they might drift for millions of years without encountering another atom, traveling across distances that dwarf the size of solar systems without experiencing a single collision or interaction. Their existence is one of profound isolation, motion without purpose, travel without destination. If time has meaning in such places, it is not the time we know from our daily lives, measured in seconds and minutes, hours and days. When nothing changes, when no events occur to mark the passage of moments, time becomes abstract, a mathematical concept rather than an experienced reality. 1,000,000 years in one of these voids is indistinguishable from a single day because nothing happens to differentiate them. The view doesn't change. The temperature doesn't fluctuate. No processes unfold that would provide a sense of progression or development. Time passes in the technical sense. The universe continues to age and evolve, but locally, in these quiet corners, that passage leaves no trace. It's as if time exists but doesn't matter, flows but doesn't affect, continues but doesn't change anything. The scale of these empty regions challenges comprehension. The distance from Earth to the Sun, about 150 million kilometers, seems vast to us. It takes light 8 minutes to cover this distance, and it would take current spacecraft years to make the journey. But this distance is nothing compared to interstellar space. The nearest star to our Sun, Proxima Centauri, is about 40 trillion kilometers away, more than 250,000 times the Earth-Sun distance. Light takes over 4 years to bridge this gap, and with current technology, a spacecraft would need tens of thousands of years to reach it. Yet even this vast distance is minuscule compared to intergalactic space. The Andromeda Galaxy, our nearest large galactic neighbor, is about 25 quintillion kilometers away. Light takes 2.5 million years to travel from Andromeda to us, and any spacecraft we could build would take billions of years to make the journey. And yet even these immense distances pale in comparison to the true voids of the universe, the supervoids that exist between galaxy clusters and superclusters. These voids can be hundreds of millions of light years across, regions so vast that entire galaxy clusters could fit inside them with room to spare, yet they contain almost nothing. A handful of small galaxies might be scattered through a supervoid, separated by distances so great that they have virtually no interaction with each other, but for the most part, these regions are simply empty. Flying through one at the speed of light, you would travel for hundreds of millions of years and see nothing change, nothing new appear, nothing to break the monotony of absolute darkness and emptiness. The largest voids in the universe stretch across distances so great that light takes hundreds of millions of years to cross them. The Boat's void, one of the largest known, spans about 330 million light-years in diameter and contains only about 60 galaxies, where a comparable volume in a typical region of the universe might contain thousands. Imagine a place where the nearest galaxy is so far away that it appears as nothing more than a faint smudge. If you can see it at all, a barely perceptible glow against the darkness that might require instruments to detect. In these voids, there are no stars being born, no planets forming, no cosmic events taking place. Everything that could happen has already happened long ago, or hasn't begun to happen yet and won't for billions of years to come. Standing at the edge of one of these cosmic voids, if such a thing were possible, would be an experience beyond any earthly comparison. You would be looking out at a darkness so complete that your eyes would search desperately for any point of reference and find none. No stars would twinkle in the distance, no galaxies would glow faintly on the horizon, no nebulae would add color or texture to the view. The void would not press in on you or threaten you. It would simply be there, indifferent and unchanging, a monument to the universe's capacity for emptiness. Hours could pass, days, years, centuries, and nothing would change. The same darkness would surround you, the same absence would extend in every direction, and the same profound silence would fill the space. It would be both terrifying and liberating, the realization that you are truly, completely alone in a way that no human has ever been alone before. Yet within that aloneness there would be a peace unlike anything available in our crowded corner of the cosmos. The peace that comes from knowing that nothing can disturb you because there is nothing nearby to do the disturbing. The peace of complete isolation, of being so far from everything else that you are effectively in your own private universe, untouched by the concerns and conflicts that animate regions where matter clusters together. This is not the peace of resolution or harmony where competing forces balance each other out, but the peace of absence where there are no forces to compete in the first place. It's a peace that asks nothing of you and offers nothing in return, that neither welcomes nor rejects you, that simply exists as the default state of most of the universe. These voids are not scars or flaws in the cosmic fabric, mistakes in the universe's construction that somehow got left empty while everything else was being filled. They're an essential part of the universe's structure, the negative space that gives definition to the clusters and filaments where galaxies gather. Just as the spaces between words are necessary for language to have meaning, the voids between structures are necessary for cosmic structure to exist. Without the voids, everything would be uniformly distributed, spread out at the same density everywhere, and there would be no galaxies, no clusters, no large-scale structure at all. The voids are as important as the structures, the silence as important as the sound, the emptiness as important as the fullness. The supervoids represent the universe at its most minimal regions where existence has been stripped down to almost nothing. In a typical region of space, you might find thousands of galaxies within a sphere 500 million light-years across, each galaxy containing hundreds of billions of stars, each star potentially hosting planets and smaller bodies. The volume of space would be crisscrossed with gas streams flowing between galaxies, lit by the glow of countless suns, stirred by the gravity of dark matter halos, and alive with the electromagnetic radiation produced by astronomical phenomena. But in a supervoid, this richness is almost entirely absent. The same volume might contain only a few dozen galaxies, scattered so thinly that they have little influence on each other, drifting through the darkness like ships passing in an infinite ocean, each unaware of the other's existence. The space between these sparse galaxies is not completely empty. No region of the universe truly is, but it approaches emptiness more closely than almost anywhere else. There might be one hydrogen atom per cubic meter, possibly even less, compared to the trillions upon trillions of atoms per cubic meter in Earth's atmosphere. At this density, matter is more a theoretical concept than a practical reality. An atom could exist for millions of years without encountering a neighbor, drifting alone through a void so large that the atom's entire trajectory, from its origin to some distant future destination, represents a journey longer than human civilization has existed. These solitary atoms are perhaps the loneliest objects in existence, cut off from any possibility of interaction or relationship, existing in a state of fundamental isolation that will likely never end. In regions of intergalactic space within galaxy clusters where galaxies are closer together and interact more frequently, there exists a thin plasma called the intercluster medium. This gas is hot, heated by the gravitational energy of the cluster to temperatures of millions of degrees, and it glows faintly in X-rays, revealing its presence to specialized telescopes. But in the supervoids, even this tenuous medium is mostly absent. The gas that exists is cold, barely above the temperature of the cosmic microwave background, and so diffuse that it might as well not be there at all. It contributes negligibly to the mass of the region, exerts no pressure to speak of, and undergoes no processes that would make it interesting or dynamic. It simply exists, spread so thinly that it is more absence than presence. The lack of matter in supervoids means that gravity, the fundamental force that shapes the universe on large scales, has almost nothing to work with. Gravity requires mass to be significant, and in regions where mass is almost entirely absent, gravity becomes negligible. An object in a supervoid would feel virtually no gravitational pull from anything, free to drift in whatever direction its initial velocity carried it, undeflected and undisturbed. This is as close to freedom from cosmic influence as anything can get, existence without constraint, motion without external direction. The object would coast through space following Newton's first law in its purest form, continuing in a straight line at constant velocity, because there are no forces acting on it to change that motion. This gravitational peace is profound because gravity is normally the dominant force in the universe on large scales. Planets orbit stars because gravity constrains them. Stars orbit galactic centers because gravity binds them. Galaxies cluster together because gravity attracts them. But in the supervoids, gravity's influence is so weak that it might as well not exist. The universe's normal hierarchical structure, where small things orbit larger things which orbit still larger things, breaks down. There is no hierarchy because there is nothing to organize. Each atom, each rare molecule, each vanishingly unlikely dust grain exists as an independent entity, unconstrained by relationships or bound by mutual attraction. It is existence reduced to individual identity, unconnected and unaffiliated. The darkness in a supervoid is of a special quality. It's not darkness caused by an absence of light sources, though that's certainly true as well. It's darkness caused by the absence of anything that light could interact with. Light passing through a supervoid would simply continue through, unscattered and unabsorbed, because there are no particles to scatter or absorb it. If you somehow shined a flashlight in a supervoid, the beam would extend forward in a perfectly straight line, undispersed and undiminished, until it eventually left the void entirely and encountered something in the denser regions beyond. There would be no visible beam, no way to see the light unless you looked directly into the source, or unless the light happened to hit your eye directly. The light would be present, photons traveling through space, but it would be invisible because there would be nothing for it to illuminate. This is darkness as fundamental absence rather than as blocked light. On Earth, even in the darkest night, there are things around us, air molecules, surfaces, the ground beneath our feet, that could reveal themselves if light were present. We know we're in darkness because we can't see these things we know are there. But in a supervoid, the darkness is not hiding anything. There is nothing there to be hidden. The darkness is not a veil over reality, but reality itself, the true state of the cosmos in regions where matter never accumulated. It's honest darkness, if such a thing can be said, darkness that represents rather than obscures. Time behaves strangely in such places, or rather our perception of time struggles when applied to environments where nothing changes. For time to have meaning in our experience, we need change to measure it by. We mark time by the motion of Earth around the sun, by the ticking of clocks, by the biological rhythms of our bodies, by the progression of events in our lives. But in a supervoid, none of these measures exist. There is no planet orbiting to mark years, no processes unfolding to mark hours, no changes occurring to distinguish one moment from another. From the perspective of an observer in a void, if such an observer could exist, the passage of time might become imperceptible. One moment would blend into the next without distinction, and the question how much time has passed would become meaningless because nothing has happened to mark that passage. Yet time does pass, at least in the abstract mathematical sense that physicists use to describe the universe. The cosmic microwave background photons that fill even the supervoids are gradually redshifting as the universe expands, their wavelengths stretching and their energy decreasing. This process is time-dependent, occurring at a rate determined by the universe's expansion, and it provides a kind of cosmic clock that ticks uniformly everywhere. But this clock marks time in the most abstract sense, a change so subtle and so universal that it provides no local reference, no way for an observer in a void to notice that anything is different than it was a moment ago. Its time is pure duration without experience, existence continuing, but not progressing. The expansion of space itself is more noticeable in supervoids than in denser regions, at least in principle. In areas where matter is concentrated, the gravitational attraction of that matter fights against the expansion, slowing it down or even reversing it locally, causing structures to collapse and form bound systems. But in the voids, where there's almost no matter to resist, the expansion proceeds at nearly its maximum rate, determined by the universe's overall properties, rather than by local gravitational effects. Space in the voids is stretching smoothly and uniformly, carrying the few atoms that exist along with it, increasing the distances between them over time. An atom that was 1 billion light-years from its nearest neighbor might find that distance increased to 1,000,000,001 light-years over the course of a few million years, a change so gradual that it would be imperceptible during any reasonable observation period, but real nonetheless. This pure expansion, uncontaminated by local gravitational effects, represents the universe's natural tendency when left alone. The Big Bang set space expanding, and in the absence of matter to slow or stop that expansion, it simply continues. The voids show us what the universe would be like everywhere if matter had never clumped together to form structures. A cosmos of uniformly expanding emptiness, growing larger with each passing moment but remaining fundamentally unchanged in its properties. It's a glimpse of a simpler universe, one that might have been if the early cosmic conditions had been just slightly different, if the tiny density fluctuations that seeded galaxy formation had never existed. In that alternative universe, there would be no galaxies, no stars, no planets, no life, just an infinite expanse of slowly expanding emptiness, peaceful in its absolute uniformity. The cosmic microwave background radiation, the relic light from the Big Bang that fills all of space, is particularly pure in the supervoids. In regions where galaxies and galaxy clusters exist, this background radiation is slightly disturbed by what astronomers call the Knyazhel-Dyevich effect, where the hot gas in galaxy clusters scatters the microwave photons and changes their energy slightly. But in the voids, where there's no hot gas to cause scattering, the microwave background retains its primordial character more fully. It arrives at any point in the void exactly as it was when it was first released, about 400,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. This radiation is a messenger from the universe's infancy, and in the voids, that message is delivered without distortion. The uniformity of the microwave background in supervoids is remarkable. If you measured the temperature of this radiation from different directions while floating in a void, you would find that it varies by only tiny fractions of a degree across the entire sky, one of the most uniform distributions known in nature. This uniformity reflects the smooth conditions in the early universe, before gravity had time to create the structures we see today, when the cosmos was a nearly homogeneous sea of matter and radiation. The voids preserve a memory of this earlier, simpler time, a reminder that the complicated, structured universe we observe is a relatively recent development in cosmic history, and that the universe's natural state, its default condition, is smooth uniformity rather than clustered complexity. An observer in a supervoid would be surrounded by this uniform glow, though glow is perhaps too strong a word for radiation so faint that it's invisible to human eyes and detectable only with sensitive instruments. The microwave background has a temperature of about 2.7 degrees above absolute zero, far too cold to see or feel, but it represents a baseline warmth that pervades the entire universe. Nothing can cool below this temperature unless actively refrigerated, because everything in the universe is bathing in this radiation, absorbing it and re-emitting it, coming into thermal equilibrium with it. In the voids where there are no other sources of energy, this radiation and the rare atoms that exist are in perfect balance, neither heating nor cooling, simply coexisting at the universe's minimum temperature. This thermal equilibrium is another form of peace, the peace of systems that have settled into balance and have no energy gradients to drive change. On Earth, we're far from equilibrium, warmed by the sun on one side and cooled by empty space on the other, with energy constantly flowing from hot to cold and driving all the processes of weather, ocean currents, and life itself. But in a supervoid, there is no such flow. Everything is at the same temperature. There are no hot spots or cold spots, no energy moving from one place to another. It's a state of maximum entropy, where the second law of thermodynamics has done its work completely and brought the system to a condition where no further change is possible. It's peace through exhaustion, the stillness that comes when all possible events have occurred and nothing new can happen. Some of the most peaceful places in the cosmos are the dark nebulae, vast clouds of dust and gas that block out the light from stars behind them. When you look at photographs of regions of our galaxy, like the Coal-Sack Nebula or Barnard's Dark Nebula, they appear as dark patches against the bright background of the Milky Way, like windows into nothingness, voids that seem to have been cut out of the star field. But these are not true voids, not empty regions like the supervoids we've discussed. Instead, they're clouds, dense collections of gas and dust, but clouds so cold and dark that they emit almost no light of their own and block the light from stars behind them. They're dark not because they're empty, but because they're full of material that absorbs light, hiding rather than revealing their presence. If you could somehow enter one of these dark nebulae, you wouldn't find yourself in complete darkness. Instead, you'd be surrounded by a faint, diffuse glow, light that has scattered through the dust particles over and over again until it spread out evenly in all directions. This light would be incredibly dim, far fainter than moonlight, perhaps comparable to starlight on an overcast night, barely enough to perceive but present nonetheless. The inside of a dark nebula is like being inside a fog, but a fog that stretches for light years in every direction, a cloud so vast that you could travel at the speed of light for years without emerging from it. The experience would be disorienting, with no visible landmarks, no sense of scale, no way to tell how far you'd traveled or how far you had yet to go. Nothing much happens in these places, at least not on timescales that humans can perceive or relate to. The dust is too cold and too spread out to collapse and form new stars, at least not yet, not for millions of years more. It just hangs there, drifting slowly through space, moved by galactic rotation and the occasional shock wave from a distant supernova, but otherwise unchanged and undisturbed. The temperature in these clouds is incredibly cold, typically around 10 to 20 degrees above absolute zero, cold enough that almost any gas that isn't hydrogen or helium would freeze solid. At these temperatures, atoms and molecules move with minimal energy, their thermal motion reduced to a sluggish crawl, and the chemistry that does occur proceeds at rates so slow that reactions might take thousands of years to complete. Within these dark nebulae, time seems to lose its urgency. The processes that do occur happen so slowly that they're imperceptible on human timescales. A dust grain might drift a few kilometers over the course of a year, an insignificant movement in a cloud that spans dozens of light years. The temperature barely fluctuates, staying cold and constant, protected from external heat sources by the layers of dust that absorb any incoming radiation. The density varies gradually across the cloud, with some regions slightly denser than others, but these variations develop over millions of years, not days or months. Any atoms or molecules that exist in these clouds move sluggishly, occasionally bumping into each other, but mostly just drifting in the darkness, following paths determined by their random thermal motions and the gentle pull of the cloud's overall gravity. These clouds are ancient. Some of them have existed for hundreds of millions of years without undergoing any significant transformation. They're witnesses to the galaxy's history, floating through it like ghosts, present but not participating, observing but not influencing. They've seen countless stars born and die in other regions of the galaxy, watched as the galaxy's spiral arms swept past them, experienced the slow rotation of the entire galactic disk as it turns around the central bulge. Yet through all this, the clouds themselves remain essentially unchanged, cold and dark and stable, patient in a way that living beings can barely conceive of. They're not waiting for anything in particular, not preparing for some future event, just existing in their current state, because that state is stable and there's no force compelling them to change. In their stillness, dark nebulae embody a kind of patience that human beings can barely conceive of, a willingness to simply exist without purpose or goal. We are creatures of action and intention, evolved to plan and strive and work toward objectives. The idea of existing without doing, of being without becoming, is alien to our nature. Yet the dark nebulae do exactly this. They exist without doing anything. They are without becoming anything else, and they've been doing so for longer than complex life has existed on Earth. Their example suggests that purposeless existence is not only possible, but might be the default state for much of the universe, that our drive to achieve and accomplish is a local and temporary phenomenon, not a cosmic truth. The dark nebulae also serve as sanctuaries for the simplest molecules in the universe. In the depths of these clouds, shielded from the harsh ultraviolet radiation that pervades most of space and would tear apart any complex molecules, delicate molecular bonds can form and persist. Water molecules, carbon monoxide, ammonia, methanol, and dozens of other simple compounds drift through the darkness, frozen to the surfaces of dust grains or floating freely in the tenuous gas. These molecules are the building blocks of complexity, the raw materials from which stars and planets, and eventually life will someday form. But here in the dark nebulae, they exist in their most basic forms, not yet assembled into anything more elaborate. Their potential waiting to be realized, possibility suspended in time, and in their waiting, there is a profound peace. They don't struggle or strive to become something more complex, don't yearn to fulfill some cosmic destiny. They simply exist, drifting and occasionally reacting with each other, forming new molecules or breaking apart into simpler components, following the rules of chemistry without any awareness or intention. They're ready to contribute to future complexity when the time comes, when the cloud eventually becomes dense enough to collapse and form stars, when the heat and pressure of star formation drives more complex chemistry. But until that time, which may be millions of years in the future, they remain simple, patient, and still, content to be what they are without striving to be more. The dust grains that fill these clouds are equally patient and equally essential. These grains are tiny, typically only a micron or less in diameter, smaller than the width of a human hair, composed of silicates and carbon compounds that condensed in the atmospheres of dying stars or formed in the shocked gas of supernova remnants. They're the ashes of stellar death, recycled material from previous generations of stars, now drifting through space, waiting to be incorporated into the next generation. Each grain is coated with a thin layer of ice, frozen water, and other volatiles that have accumulated on its surface over millions of years as molecules randomly collided with it and stuck. These icy mantles protect the grains and provide surfaces where molecular chemistry can occur, where atoms can meet and bond in ways that would be impossible in the gas phase. A single dust grain in a dark nebula might exist for millions of years without experiencing any significant event. It drifts slowly through the cloud, occasionally colliding with another grain and perhaps sticking to it, gradually accumulating into larger aggregates over vast timescales. It absorbs the faint starlight that manages to penetrate into the cloud and re-radiates that energy as infrared heat, but at such low temperatures that the emission is feeble and contributes little to the cloud's energy budget. The grain experiences no drama, no sudden changes, no catastrophic events. Its existence is one of profound monotony, the same conditions continuing day after day, year after year, millennium after millennium, with no variation to mark the passage of time. Yet despite their apparent inactivity, dark nebulae play a crucial role in the galactic ecosystem. They're repositories of matter, storehouses where the galaxy keeps its raw materials between periods of star formation. When conditions eventually become right, when the cloud is compressed by a passing shock wave or disturbed by the gravity of a nearby star cluster, these peaceful regions will become sites of violent starbirth, the tranquility shattered by the onset of gravitational collapse. But until that moment arrives, they remain at peace, preserving the matter that will someday become new stars and planets, protecting it from the hazards of the more active galactic environment, keeping it safe and cold and unchanged until it's needed. The transition from peaceful cloud to active star-forming region is not abrupt, but gradual, taking place over millions of years. First, the cloud begins to contract under its own gravity, pulled inward by the combined mass of all its particles. This contraction is imperceptibly slow at first, the cloud shrinking by perhaps a few percent over the course of 1,000,000 years, barely noticeable, even if you were watching closely. As the cloud contracts, it fragments into smaller clumps, each clump contracting independently, competing with its neighbors to accumulate mass. Within these clumps, the density increases, the temperature begins to rise, and the conditions start to become less peaceful. But even as the cloud progresses toward star formation, much of its volume remains in the old peaceful state, untouched by the changes occurring in the densest regions, still cold and dark and quiet. The regions of dark nebulae that will never form stars, the areas too diffuse to ever collapse, the outer layers that will be dispersed when star formation in the core begins, these regions will return to the general interstellar medium. Their brief stint as part of a cloud ended, their matter redistributed to join the thin gas that fills the space between stars. They will have spent millions of years as part of the nebula, existed in its cold and peaceful environment, and then moved on to other states, other configurations, other roles in the galactic cycle. Their time in the nebula was just one phase in an endless series of transformations, but it was a peaceful phase, a respite between more energetic states, a period of rest in matter's endless journey through the cosmos. Even within galaxies where stars cluster together in their billions, and where the pace of cosmic activity is far greater than in intergalactic space, there are quiet places. Between the spiral arms where new stars are constantly being formed in great stellar nurseries, there are gaps where the stellar population is thin and the pace of life slows to a crawl. These inter-arm regions don't get much attention from astronomers because there's nothing particularly dramatic happening in them, no bright nebulae glowing with the light of newly born stars, no supernova remnants expanding outward from recent stellar deaths. But that's precisely what makes them peaceful: the absence of drama, the lack of violent processes, the stability that comes from being in a region where most of the action has already happened elsewhere. Old stars drift slowly through these inter-arm spaces, barely interacting with one another, following predictable orbits that they've traced out countless times before. These are typically low-mass stars, red dwarfs and orange dwarfs that burn their fuel so slowly they can continue for trillions of years, far longer than the current age of the universe. The light from these ancient suns is steady and unchanging, neither growing brighter nor dimming, just continuing to shine as they have for billions of years, and as they will continue to shine for billions more. These stars have reached a state of equilibrium, burning their fuel at a rate so controlled and steady that they could continue for eons more without any significant change. They are the universe's examples of sustainable existence, neither consuming resources recklessly nor fading into premature darkness. In these inter-arm regions, the night sky from any planet would tell a story of solitude and space. Instead of being crowded with brilliant neighbors and glowing nebulae, as would be the case for a planet in a spiral arm, the view would be more sparse, more contemplative. Each visible star would stand out individually, not lost in a crowd but distinct and separate, its own point of light with space around it to breathe. The darkness between the stars would be more prominent, more noticeable, reminding any observer that emptiness is the universe's default state, and that light is the exception rather than the rule. This is the kind of neighborhood where contemplation comes naturally, where the vastness of space is evident in every direction, and where the questions that arise are about existence itself rather than about the immediate and the urgent. Our own solar system resides in such a region, between two of the Milky Way's spiral arms in what's called the Orion Spur, or local spur, a minor arm structure that connects the larger Perseus and Sagittarius arms. This location may have been essential to our development, giving us the stability and peace necessary for complex life to evolve over billions of years without being disrupted by cosmic catastrophes. In a spiral arm where stars are more densely packed, the risks would be greater. Nearby supernova might bathe our planet in deadly radiation. Close encounters with other stars might disturb the orbits of comets in the outer solar system and send them plunging toward the inner planets, and the general crowding might lead to more frequent gravitational disturbances. But in our quiet inter-arm location, these risks are minimized. We're far enough from potential threats that we've been able to develop undisturbed. The edges of galaxies represent another sanctuary of cosmic calm. While the centers of galaxies are crowded and chaotic, filled with tightly packed stars and sometimes harboring supermassive black holes that create violent phenomena, the outer regions are sparse and tranquil. Stars here are scattered widely, separated by distances that would take light years to cross, moving through space with plenty of room around them. They orbit the galactic center at a leisurely pace, taking hundreds of millions of years to complete a single circuit, traveling along paths that carry them through regions of low stellar density, where encounters with other stars are extraordinarily rare. Out here, away from the bustle of the galactic core and the crowded spiral arms, the universe feels spacious and unhurried. The gravitational influence of the galaxy as a whole is still felt, keeping these outer stars in their orbits, but locally the environment is remarkably free of constraints. A star in the galactic outskirts might go its entire lifetime without passing within a light year of another star, maintaining its solitary existence from birth to death. Any planets orbiting such a star would experience conditions of remarkable stability, with no nearby stellar neighbors to perturb their orbits, no local sources of intense radiation to worry about, no cosmic events likely to occur in their immediate neighborhood. It would be a lonely existence in some ways, but also a safe and predictable one. The night sky from a planet orbiting one of these outer stars would be a study in minimalism, with only a handful of nearby stars visible as individual points of light, and the rest of the galaxy appearing as a faint glow on the horizon. The dominant feature of the sky would be darkness, vast and uninterrupted, punctuated by only the most distant galaxies appearing as barely perceptible smudges at the limits of perception. This would be a sky that inspires awe not through its richness but through its emptiness, not through what it shows but through what it doesn't show, the vast distances and spaces that separate the rare points of light. An observer on such a world might develop a very different relationship with the cosmos than we have, seeing it less as a crowded place full of objects and more as a mostly empty place where objects are rare exceptions. The far reaches of galactic halos contain another population of peaceful wanderers, the ancient stars that orbit high above and below the galactic plane in elliptical paths that carry them far from the crowded disk. These halo stars were among the first to form in the universe, created from the primordial hydrogen and helium that existed before any stars had enriched the cosmos with heavier elements through fusion and supernova explosions. They're relics from a younger universe, metal-poor stars that contain almost none of the elements beyond hydrogen and helium, and their chemistry reflects the simpler conditions of cosmic youth. Their orbits carry them on long, elliptical paths that take them far from the crowded galactic disk where most stars reside, and during the portions of their orbits that carry them through the halo, these stars spend eons in near total isolation. A halo star might have an orbit that takes it 50,000 light-years above the galactic plane, far beyond the disk where most of the galaxy's visible matter resides. From this vantage point, the galaxy would appear as a luminous disk far below, slowly rotating over millions of years, its spiral arms gradually shifting position as stars and gas clouds move through them. The star itself would move in silence through the dark halo, passing occasionally through clouds of dark matter that it cannot see and does not interact with except through gravity's gentle pull, following an orbit that was determined billions of years ago when the star first formed, and that has changed little since then. The halo is not completely empty. It contains gas at a very low density, dark matter that makes up most of the mass, and occasional globular clusters, but these components are spread so thinly that the dominant impression is one of emptiness and solitude. A planet orbiting one of these halo stars would offer its inhabitants a unique perspective on existence, a view from outside the galactic mainstream, where the great spiral of stars that dominates the universe for most beings appears as a distant object, beautiful but remote. Life on such a world would develop with a profound sense of cosmic isolation, knowing that they are separated from the galaxy's heart not just by distance, but by a fundamental difference in circumstance. They would be outsiders, observers rather than participants, watching the galaxy from afar but not really part of it in any meaningful sense. The night sky would be dominated by darkness, with the galaxy itself appearing as a band of light across the sky, faint and distant, and the rest of the sky would show only the most distant galaxies, faint smudges barely visible against the darkness. The halo stars have witnessed the entire history of their galaxy from this distant perspective, observing but not participating in the drama of galactic evolution. They've seen the galaxy grow through mergers with smaller galaxies, watched as the disk formed and developed its spiral structure, observed the birth and death of countless generations of stars in the disk below. Yet they've remained largely unchanged themselves, following their same orbits, maintaining their same properties, neither growing nor fading in any significant way. They're living fossils, preserving in their composition and motion the conditions of the early universe, carrying information about cosmic history in their very atoms and orbits. In their stability and their longevity, they embody a kind of peace that comes from having found a stable state and maintaining it across cosmic timescales. Globular clusters, dense spherical collections of hundreds of thousands or millions of ancient stars that orbit in the halos of galaxies, represent another form of peaceful existence despite their crowded cores. These clusters are among the oldest structures in galaxies, formed when galaxies themselves were young, and they've been following their elliptical orbits through the halo ever since. The stars within globular clusters are all roughly the same age, all formed together from the same cloud of gas, and they've been orbiting their common center of mass for billions of years, a gravitationally bound family that has stayed together since birth. While the centers of these clusters are indeed packed with stars, with densities far higher than in typical regions of a galaxy, the outer regions are more sparse, and the overall motion of the cluster through space is peaceful and predictable. Within a globular cluster, time is measured in orbital periods, the time it takes a star to complete one circuit around the cluster's center. These periods might be hundreds of thousands or millions of years, depending on the star's distance from the center and the cluster's overall mass and size. From the perspective of an inhabitant of a planet within such a cluster, the sky would be rich with stars, hundreds or thousands visible to the naked eye, far more than we can see from Earth, creating a spectacular night sky that would cast enough light to read by. Yet these stars would maintain almost constant positions relative to each other, moving so slowly in their orbits that generations could pass without any noticeable change in the stellar patterns. The cluster would provide a sense of stability and permanence, a cosmic neighborhood that has existed unchanged for longer than most galaxies have had their current forms. The collective motion of a globular cluster through the galactic halo is itself a kind of meditation on peaceful existence. These clusters follow elliptical orbits that carry them high above and below the galactic plane, passing through the disk occasionally, but spending most of their time in the quiet regions of the halo. Their orbits take hundreds of millions of years to complete, and they've likely completed dozens or even hundreds of such orbits during their long lifetimes, billions of years during which the orbits have remained essentially unchanged. Each orbit is similar to the last, a predictable path through space that varies little from one cycle to the next, traced out with the regularity of a cosmic metronome. The cluster experiences no seasons, no changes in environment, except for the brief periods when it passes through the galactic disk, just the slow, steady rhythm of its orbit, a cosmic heartbeat that has been beating for longer than complex life has existed on Earth. Perhaps the most profoundly peaceful places in the cosmos are the remnants of dead stars that have cooled completely, or are in the long process of cooling toward absolute zero. When certain types of stars die, they don't explode or collapse into black holes. Instead, they simply fade away, gradually radiating their remaining heat into space until they become cold, dark objects floating silently through the void. These stellar corpses represent the final state of matter for many stars, the end point of stellar evolution, the last chapter in a story that began with brilliant ignition and ends in quiet darkness. They no longer shine, they no longer warm anything around them, and they no longer change in any meaningful way. They've reached a state of perfect equilibrium with their surroundings, neither giving off significant energy nor receiving any. In a sense, they've achieved the ultimate peace, having finished their long journey from brilliant youth to quiet old age. White dwarfs are the most common type of stellar remnant, the fate awaiting stars like our sun when they exhaust their nuclear fuel. When a sun-like star runs out of hydrogen in its core, it swells into a red giant, then sheds its outer layers into space, leaving behind a dense core of carbon and oxygen about the size of Earth, but containing roughly the mass of the sun. This white dwarf is incredibly hot initially, with surface temperatures that can exceed 100,000 degrees, but it has no internal source of energy. It's not undergoing fusion, not generating new heat, just radiating away the thermal energy it accumulated during its active lifetime. This cooling process is incredibly slow, taking billions of years for a white dwarf to cool from its initial temperature to something approaching the temperature of the cosmic microwave background. The process of becoming a black dwarf, a white dwarf that is cooled completely and no longer emits any perceptible light or heat, takes far longer than the current age of the universe. Current calculations suggest it would take trillions of years for a white dwarf to cool to the point where it's effectively invisible and at thermal equilibrium with its surroundings. This means that black dwarfs don't actually exist yet in our universe. They're a theoretical endpoint that the cosmos is slowly working toward, a future state that won't be realized until the universe is vastly older than it is now. But white dwarfs themselves represent a stage well along the path to ultimate peace, stellar remnants that have left behind the turbulent fusion-driven existence of normal stars and entered a long, quiet period of cooling that will continue for timescales that dwarf all of recorded human history. These cooling stellar remnants are incredibly dense, packing a mass comparable to the Sun into a sphere the size of Earth. The matter inside them is in a state called electron degeneracy, where the electrons are packed so tightly that quantum mechanical effects prevent them from being compressed further. This gives the white dwarf a strange rigidity. It's not held up by thermal pressure like a normal star, but by quantum mechanical pressure that doesn't depend on temperature. As a result, the white dwarf doesn't collapse as it cools. It simply becomes a colder version of itself, maintaining its size and structure even as its temperature drops. The surface gradually crystallizes, forming what might be the largest crystals in the universe, structured lattice of carbon and oxygen atoms extending throughout the entire stellar remnant, creating a cosmic diamond the size of a planet. Yet despite this density and these exotic properties, white dwarfs are remarkably stable and unchanging once they've finished their initial adjustment period after formation. They don't undergo fusion, don't experience the turbulent processes that characterize active stars, and don't interact much with their surroundings unless they happen to be in a binary system with a companion star that feeds them matter. They simply sit in space, slowly cooling, their only activity the gradual radiation of stored heat into the cosmic void. This radiation is so slow that measuring changes in a white dwarf's temperature would require observations spanning millions of years. To an observer watching a white dwarf, it would appear essentially frozen, unchanging, eternal, a monument to stellar death rendered in compressed matter. Orbiting a white dwarf, if you could somehow survive the environment, and if the remnant had retained any planets from its previous existence, would be an experience of profound stillness. The dwarf would provide no warmth worth mentioning, at least not after it had cooled for a few billion years. No variation in light would mark seasons or cycles. No stellar activity would create space weather or auroras. No changes would occur to mark the passage of time. The star's surface would be smooth and featureless, lacking the granulation and sunspots and flares that characterize normal stars, just a uniform sphere slowly radiating away its residual heat. The space around it would be equally quiet, cleared of most debris by the star's violent death throws long ago when it shed its outer layers, leaving only perhaps a few remaining planets or asteroids in distant, stable orbits. This system would represent a kind of afterlife for stellar systems, the peaceful phase that follows the drama and activity of the star's main sequence lifetime. Everything urgent has already happened. All the energy has been spent, all the dramatic events have occurred, and what remains is simply the slow thermal decay toward equilibrium with the cosmic background. Any planets that survived the red giant phase would be frozen worlds, their surfaces at temperatures barely above absolute zero, Any atmospheres long since frozen solid and collapsed to the surface. Any geological activity ceased billions of years ago when internal heat sources were exhausted. These worlds would be museums preserving in their frozen geology the history of the system, unchanged and unchanging for timescales longer than current stellar lifetimes. Brown dwarfs, objects too small to ignite hydrogen fusion and become true stars, represent another form of cosmic peace. These failed stars exist in a state of perpetual adolescence, never achieving the nuclear ignition that would transform them into brilliant suns, but also never fully cooling into the darkness of planetary status, at least not for timescales far longer than the universe's current age. They glow faintly in infrared light, radiating the heat left over from their formation and whatever heat they generate through the slow fusion of deuterium in their cores. But this glow is so dim that they're invisible to the naked eye, even from relatively close distances. Brown dwarfs drift through the galaxy in solitude, neither part of stellar populations in any meaningful sense, nor associated with planetary systems in most cases. They're the universe's loners, objects that fell between the categories, too massive to be planets, but too small to be stars. The existence of a brown dwarf is one of slow and gentle decline. It forms from a collapsing cloud of gas, just as a star does, contracting under its own gravity and heating up as gravitational potential energy is converted to thermal energy. But it lacks the mass necessary to achieve the core temperatures and pressures required for sustained hydrogen fusion, the process that powers normal stars. It might briefly fuse deuterium, a heavy isotope of hydrogen that ignites at lower temperatures, but this fuel is quickly exhausted, burning out in a few million years and leaving the brown dwarf to live on stored heat alone. From that point forward, the brown dwarf simply cools, following the inexorable laws of thermodynamics, radiating its heat into space at a rate determined by its size, composition, and surface temperature. The cooling timeline for a brown dwarf extends across billions of years. Initially bright and infrared, glowing with the heat of formation and whatever fusion occurred, the brown dwarf gradually fades as it cools, transitioning from red to brown to eventually becoming a cold, dark object, indistinguishable from a massive planet. Throughout this long decline, the brown dwarf experiences no drama, no sudden changes, no catastrophic events. Its evolution is smooth and predictable, determined entirely by the simple physics of heat radiation and gravitational contraction. For any observer monitoring a brown dwarf over cosmic timescales, the experience would be one of watching entropy in action, observing the slow but certain march toward thermal equilibrium, seeing a once warm object gradually come into balance with the cold of space. The space between brown dwarfs and other objects is typically vast, as these dim objects are hard to detect, and thus their distribution in the galaxy is not well understood, but they're likely quite common, possibly outnumbering normal stars in some mass ranges. They move through the darkness alone, their faint infrared glow illuminating nothing, noticed by nothing, influencing nothing beyond their immediate gravitational neighborhood. If planets exist around brown dwarfs, and some have been detected, they would be cold worlds indeed, receiving minimal warmth from their dim parent object and existing in perpetual twilight at best, with no bright sun to warm them and no day-night cycle in the traditional sense. The pace of time on such worlds would seem to slow, with the already dim brown dwarf fading even further over millions and billions of years, marking geological eras rather than seasons or years. Neutron stars, the incredibly dense remnants of massive stars that have exploded as supernova, might seem like unlikely places of peace given their extreme properties. These objects are among the strangest in the universe, packing more mass than the Sun into a sphere only about 20 kilometers across, rotating potentially hundreds of times per second in their youth, and possessing magnetic fields trillions of times stronger than Earth's. Young neutron stars, particularly those that are pulsars, are violent and energetic, emitting beams of radiation that sweep across space like lighthouse beams, powered by the star's rotational energy and fierce magnetic fields. But as neutron stars age, they gradually slow down, their intense activity diminishing over millions of years as they radiate away, their rotational energy and their magnetic fields decay. An ancient neutron star, billions of years old, would be a very different object from a young pulsar. It would have slowed its rotation to perhaps once every few seconds or even longer, no longer spinning fast enough to generate the relativistic beams that characterize pulsars. Its magnetic field would have decayed to a small fraction of its initial strength, no longer capable of accelerating particles to extreme energies or creating the complex magnetosphere that young neutron stars possess. The star would have stopped emitting the intense radiation that characterizes younger pulsars. Its only output, the faint thermal radiation from its cooling surface. In every way that matters, the ancient neutron star would have become quiet, having exhausted the energy sources that made it active, and settled into a long period of cooling that will continue for trillions of years. The surface of an ancient neutron star, if you could somehow observe it up close, would be a landscape unlike anything else in the universe. The gravity at the surface is so intense, about 100 billion times stronger than Earth's, that it pulls the surface almost perfectly smooth. Any mountains or irregularities would be only millimeters high at most, flattened by gravity so strong that it would crush normal matter instantly. The surface might be a crystalline solid, a lattice of atomic nuclei immersed in a sea of electrons, or it might be a sea of superfluid neutrons covered by a thin crust of heavier nuclei. The exact composition is uncertain because we cannot create such extreme conditions in laboratories. Whatever it is, it would be remarkably uniform and unchanging, a surface that reflects the deep equilibrium the neutron star has achieved with its internal structure and external environment. The space immediately around a neutron star shares in this eventual peace. In the star's youth, the region surrounding it would have been filled with high-energy particles, intense radiation, complex magnetic field structures, and possibly a pulsar wind nebula created by the outflow of relativistic particles. But as the neutron star ages and quiets, this environment becomes calmer. The deadly radiation subsides, the magnetic field weakens and becomes less complex. The particle acceleration ceases, and the space around the star becomes merely empty rather than actively hostile. Any objects that somehow survived the supernova that created the neutron star, or that wandered into the system afterward, would find that with time their environment becomes increasingly benign. They would orbit a dark, quiet star, receiving no light beyond faint thermal radiation and little radiation of any kind, existing in a stillness broken only by the steady pull of immense gravity. Rogue planets, worlds that were ejected from their solar systems and now wander through interstellar space alone, represent another form of cosmic isolation that approaches absolute peace. These planets no longer orbit any star, having been flung out of their birth systems by gravitational interactions with other planets or by close encounters with passing stars. They drift through the darkness, receiving no light and no warmth from any nearby source, their surfaces frozen to temperatures barely above absolute zero. Without a sun to provide energy, there would be no weather on these worlds beyond the occasional impact of interstellar dust particles, no erosion beyond the slowest geological processes, no cycles of day and night, no seasons marking the passage of time. If you could stand on the surface of one of these rogue worlds, you would see a sky completely devoid of any bright objects, just the faint glow of distant galaxies scattered across the heavens like barely perceptible mist. It would be the loneliest view in the universe, but also perhaps the most peaceful, a world where nothing disturbs the silence and nothing interrupts the darkness. The sky would be darker than anything we can experience on Earth, where even on the darkest night the atmosphere scatters some light and nearby celestial objects are visible. On a rogue planet in deep interstellar space, the only light would come from distant galaxies, so faint that they would be at the limit of perception even in perfect darkness, and from the cosmic microwave background, which is far too dim to see with human eyes. The overwhelming impression would be of darkness, complete and total, a darkness so profound that it would feel almost physical, as if you were surrounded by a solid substance rather than empty space. The surface of a rogue planet would be a landscape frozen in time, preserved exactly as it was when the planet was ejected from its system, perhaps billions of years ago. Without a sun to provide energy, there would be no weather, no wind to erode features, no rain or water flow to reshape the terrain, no freeze-thaw cycles to crack rocks. Any features that existed would remain unchanged for billions of years, a permanent record of the planet's last days in its original solar system. Mountains would stand unweathered, craters would remain sharp-edged and fresh-looking, and any geological formations would be preserved as if frozen at the moment of ejection. If the planet once had an atmosphere, it would have frozen and fallen to the surface as snow, creating a layer of solid nitrogen, oxygen, carbon dioxide, or whatever gases had made up the atmosphere, covering the ground in a smooth, frozen blanket. This frozen atmosphere would lie undisturbed, a layer perhaps meters or even kilometers thick, depending on the original atmospheric density, creating a surface unlike anything in our solar system. Walking across such a surface, if it were somehow possible, would be like walking through a museum where everything is perfectly preserved, where the past remains present because no processes exist to transform it into something new. Your footsteps would leave permanent marks in the frozen gas, tracks that would remain visible for billions of years because there's no wind to erase them, no geological activity to cover them, no processes of any kind to disturb them. You would be the first visitor this world has had since its ejection, and likely the last it will ever have, moving through a landscape that has seen nothing and experienced nothing for longer than complex life has existed anywhere in the universe. Deep within a rogue planet, beneath kilometers of frozen surface material, there might still be warmth, a last holdout against the cosmic cold. The planet's interior, heated by radioactive decay of elements like uranium, thorium, and potassium, and warmed by residual heat from the planet's formation, could maintain temperatures above freezing, despite the frigid surface. This internal heat dissipates slowly, conducted through the planet's rocky mantle and escaping through the frozen surface at a rate so gradual that it could sustain warm conditions in the deep interior for billions of years. If the planet had enough internal heating, it could maintain liquid water oceans beneath ice shelves hundreds of kilometers thick, similar to the subsurface oceans thought to exist on Europa and Enceladus in our own solar system, but completely isolated from any external energy source. These subsurface oceans, if they exist, would be completely isolated from the cosmos, sealed beneath ice and rock, existing in absolute darkness. No light from any star would ever penetrate to these depths. No external energy would drive any processes there. No connection would exist with the universe beyond the planet itself. Yet they would be peaceful in their own way, immune to the cosmic catastrophes that might affect surface environments, stable over geological timescales far exceeding those of surface conditions, and potentially providing havens where exotic forms of life could exist independent of any star. These hidden oceans would be universes unto themselves, small pockets of liquid warmth in the cosmic cold, unknown and unknowable to external observers, pursuing their own slow evolution in perfect isolation, following whatever physical and possibly biological processes can occur in conditions of perpetual darkness and complete isolation. The paths of rogue planets through the galaxy are lonely trajectories that will likely never end in any meaningful sense. These worlds will drift through interstellar space for the entire remaining lifetime of the universe, perhaps occasionally passing near other star systems but never being captured, their velocities typically too high and their trajectories too random for gravitational capture to occur. They might pass through molecular clouds, spending millions of years traversing regions of slightly higher gas density, but even this would not significantly affect their journey. The gas in molecular clouds is far too thin to slow them down, and the clouds themselves are too diffuse to gravitationally capture them. The rogue planets will simply continue moving through space according to their initial velocity and the galaxy's overall gravitational field, independent agents in a universe where most objects are bound to something larger. Their journeys are not adventures but exiles, permanent separation from the stellar families they once belonged to, but in this exile there is a kind of freedom. Rogue planets are not bound by orbits, not constrained by the gravitational demands of a parent star, not subject to the variations in heat and light that affect normal planets. They chart their own courses through the galaxy, going where their initial velocity and the galaxy's gravity take them, independent agents in a universe where most objects are bound in hierarchical relationships. There's something almost noble about these lonely worlds, cast out from their homes but continuing onward, maintaining their identity and integrity across cosmic timescales, surviving in the harshest environment imaginable through nothing but their own internal resources. Comets in the outer reaches of their orbits, billions of kilometers from the sun they orbit, experience a similar isolation during the long portions of their orbits that carry them to the solar system's edge. At aphelion, the furthest point in their elliptical paths, these icy bodies move slowly through space, taking years or even decades to cover distances that they would cross in days when near the sun. The solar radiation that creates their spectacular tails when they approach the inner solar system is reduced to almost nothing at these distances, leaving the comets as cold, dark, inert lumps of ice and rock, looking nothing like the bright visitors that occasionally grace our skies. They're still technically part of their solar system, still bound by the sun's gravity even at these enormous distances. But the connection is tenuous, a thread so fine that it's almost imperceptible, a gravitational influence so weak that it takes years for the comet to noticeably change its trajectory in response. For the years or decades that a comet spends in the outer solar system, making the long, slow journey from aphelion back toward perihelion, it exists in a state of suspended animation, frozen solid with no activity whatsoever, inactive and profoundly quiet. The surface temperature hovers just a few degrees above absolute zero. The ices are locked solid with no sublimation occurring, and the interior is frozen throughout. Nothing happens on these distant bodies. No jets of gas erupt from their surfaces, no comas form around them, no tails stream out behind them. They're dormant, waiting for the eventual return to the inner solar system, where the sun's warmth will once again trigger activity. But until then they remain in cold storage, preserved in nearly pristine condition by the absolute cold of the outer solar system. The Oort cloud, a theoretical sphere of comets surrounding our solar system at distances up to a light year from the sun, represents one of the solar system's most peaceful regions, if it exists, as astronomers believe. This cloud would contain trillions of comets, icy bodies left over from the solar system's formation, but they would be spread so thinly through such a vast volume that the average distance between neighbors might be tens of millions of kilometers. Each comet would drift in its own private corner of space, following an orbit so large that it takes millions of years to complete, barely aware of the sun's existence and completely isolated from its fellow comets. The sun at that distance would appear as little more than a bright star, not noticeably brighter or larger than the other stars in the sky, certainly not warm enough to have any significant effect on the comet's surface temperature or activity. These objects move so slowly in their distant orbits that their orbital periods can be measured in millions of years. A comet in the outer Oort cloud might complete less than one orbit during the entire lifetime of complex life on Earth, traveling so slowly and through such a large orbit that centuries would pass between its successive passages through any given point in space. Time for these comets is not measured in human scales of days or years, but in geological and astronomical scales of millions of years. They're among the slowest moving objects in the solar system, paradoxically both bound to the sun by gravity, yet so distant and so slow that their connection seems more theoretical than practical, acknowledged in orbital mechanics, but barely felt in any physical sense. The concept of cosmic peace extends even to the structure of space-time itself in regions far from massive objects. Near stars, planets, and especially near black holes, space-time is warped and curved by the presence of mass and energy. This curvature creates gravitational effects, causes time to flow at different rates depending on the strength of the gravitational field, and makes the geometry of space itself complex and interesting to physicists. But in the vast empty regions between galaxy clusters, far from any significant concentrations of matter, space-time approaches its most relaxed state, a gentle, almost flat geometry that extends uniformly in all directions. Here, the fabric of reality itself is at rest, neither stretched nor compressed, neither accelerated nor decelerated by nearby masses, simply existing in its most natural and unperturbed configuration. In these regions of flat space-time, the relativistic effects that fascinate physicists and that become dramatic near massive objects become negligible to the point of irrelevance. Time flows at its standard rate, not slowed by gravitational time dilation, not affected by the curvature that massive objects create in the space-time around them. Space extends uniformly in all directions, with distances meaning exactly what Euclidean geometry says they should mean, not distorted by the presence of nearby masses. Light travels in perfectly straight lines, not bent by gravitational lensing, not following the curved geodesics that characterize its path near galaxies and galaxy clusters. This simplicity is itself a kind of peace, a relief from the complications that mass and energy introduce wherever they exist in significant quantities, a return to the baseline state of space-time when it's left alone. The universe, when freed from the influence of matter and radiation, relaxes into a state of perfect geometric tranquility. This is space-time in its pure form, the stage on which cosmic events play out, but a stage that has its own properties and its own preferred state. That preferred state is flat, or very nearly so, with only the gentle curvature introduced by the universe's overall mass-energy content and expansion. In the voids, we see space-time approaching this ideal state, showing us what the universe's geometry would be like everywhere if matter had never clumped together, if the density fluctuations in the early universe had never grown into the structures we see today. It's a simpler cosmos, one where the complications of gravity and curvature are minimized, where the laws of physics take their simplest form. The quantum vacuum, the lowest energy state of empty space, has its own form of peace despite the strange quantum fluctuations that theoretical physics tells us occur there, even in the absence of any particles or fields. Even in the most perfect vacuum, even in regions completely devoid of matter and classical electromagnetic fields, quantum field theory predicts that particle-antiparticle pairs constantly pop into existence and annihilate each other over timescales so short that they cannot be directly observed, existing only as virtual particles that borrow energy from the vacuum for infinitesimally brief moments before returning it. Yet these fluctuations average out to zero over any measurable time period. They create no net change, no lasting effect, no permanent disruption of the vacuum state. The vacuum maintains its identity, despite this quantum frothing at the smallest scales, remaining fundamentally unchanged even as it seethes with virtual activity at dimensions far smaller than atoms and times far briefer than any measurement could detect. It is peace on the macro scale built from activity on the quantum scale, stability emerging from underlying flux, constancy arising from perpetual change that cancels itself out. The vacuum teaches us that perfect stillness might not mean the absence of all motion, but rather motion that is so perfectly balanced that it creates no net effect, fluctuations that always return to equilibrium, changes that never accumulate into anything lasting. This quantum peace of the vacuum is perhaps the deepest form of cosmic tranquility, existing not despite activity, but through activity that perfectly balances itself. The vacuum is like a perfectly calm lake that might have currents and eddies beneath its surface, but presents a mirror-smooth face to the sky above. The depths might be active with quantum processes, with virtual particles appearing and disappearing, with fields fluctuating around their minimum values, but the overall state remains one of peace, the ground state from which all other states represent excitations and departures. the smooth distribution of dark energy, the mysterious force or property of space itself that drives the universe's accelerating expansion, represents perhaps the most fundamental form of cosmic peace. Unlike matter and radiation, which clump together into galaxies, stars, and planets, dark energy appears to be perfectly uniform, the same everywhere in space, unchanging over time, at least as far as we can measure. It doesn't interact with anything except through its effect on the expansion of space, doesn't respond to gravity by clustering, doesn't form structures of any kind. It simply exists, providing a constant outward push that causes space itself to expand at an ever-increasing rate, acting as a kind of cosmic constant that pervades the universe uniformly. In its absolute uniformity and its complete non-interaction with ordinary matter and radiation beyond its gravitational effect, dark energy embodies a kind of ultimate peace, existence without influence in the traditional sense, presence without participation in the complex interactions that characterize matter and energy. Dark energy doesn't care about the structures that matter forms, doesn't respond to the presence of galaxies or voids, doesn't change its properties based on local conditions. It's the same in the densest galaxy cluster as it is in the emptiest supervoid, maintaining perfect uniformity across all scales and all environments, the ultimate expression of cosmic democracy, where every location is treated exactly the same. Dark matter halos, invisible structures that surround galaxies and galaxy clusters and that contain far more mass than all the visible matter we can observe, create another realm of cosmic peace. We cannot see dark matter directly because it doesn't emit, absorb, or scatter light in any way we can detect. It doesn't interact electromagnetically, doesn't participate in the processes that make ordinary matter visible and tangible. Yet these halos are enormous, extending far beyond the visible boundaries of galaxies, containing the majority of a galaxy's total mass, and they play a crucial role in holding galaxies together and in shaping the universe's large-scale structure through their gravitational influence. Within these halos, dark matter particles follow orbits determined solely by gravity, passing through each other and through ordinary matter without interacting beyond the mutual gravitational pull, like ghosts moving through walls. They exist in a parallel reality of sorts, present alongside the visible universe but not participating in its electromagnetic affairs, influencing but not influenced except by gravity, shaping but not shaped by the processes that transform ordinary matter. These particles have been following their orbits since the early universe, undisturbed by the dramatic events that have shaped the visible cosmos, maintaining their courses through billions of years without experiencing the collisions, mergers, and transformations that characterize ordinary matter. The existence of a dark matter particle is perhaps the ultimate expression of cosmic solitude. These particles have likely never interacted with anything except through gravity since they formed in the early universe, shortly after the Big Bang. They don't scatter light, don't collide with each other in any meaningful way beyond gravitational interactions, don't undergo any of the complex chemical and physical processes that characterize ordinary matter. They simply exist and move, tracing out orbits in the gravitational potential wells created by the collective mass of all matter, both dark and ordinary, contributing their mass to cosmic structure, but never participating in the details, in the drama of stars and planets and life. In a sense, dark matter lives in the universe, but is not truly part of it in the way that ordinary matter is present, but not engaged, influential, but disconnected. If we could somehow perceive dark matter directly, see it with eyes sensitive to its presence, rather than blind to it as our physical eyes are, we would see that it fills the universe more thoroughly and more uniformly than ordinary matter does. The dark matter halos of galaxies overlap and interpenetrate, creating a cosmic web that connects all structures in ways that are invisible to conventional observations. Yet, despite this ubiquity, dark matter remains peaceful because it cannot interact in complex ways. It cannot form structures more complex than diffuse halos and filaments, cannot generate energy through processes like fusion or chemical reactions, cannot evolve into anything other than what it already is: ancient light. Photons that have been traveling through space for billions of years without interacting with anything represents another form of cosmic peace, the peace of uninterrupted journey across vast distances and times. When a photon is emitted from a distant galaxy billions of light years away, it begins a journey that might last longer than Earth has existed, traveling at the speed of light through mostly empty space, crossing voids and passing between galaxy clusters, maintaining its identity and properties over cosmic timescales. From the photon's own perspective, due to the effects of special relativity, the journey is instantaneous. Its emission and absorption are simultaneous events, separated by no time at all. But from our perspective, watching that photon's journey through the universe, we see it crossing vast distances over billions of years, a patient traveler that never tires and never stops. These traveling photons are messengers from the past, carriers of information about distant places and ancient times, and in their long journeys through empty space, they experience a form of existence that is pure motion without interaction. They don't collide with atoms because space is so empty, don't get scattered by dust clouds except in rare circumstances, don't lose energy except through the cosmological redshift caused by the expansion of space itself. They simply travel, covering distance at the maximum speed the universe allows, heading in whatever direction they were emitted, continuing until they finally encounter something that absorbs them and ends their journey. The photons that make up the cosmic microwave background have been traveling even longer, journeying through space for over 13 billion years, since they were released when the universe was only about 400,000 years old. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, making space transparent to light where it had previously been opaque. The photons that were freed at that moment have been traveling ever since, stretched to longer wavelengths by the expansion of space, cooled from the visible and infrared light they were originally to the microwave radiation they are now, but still carrying the same information they always have about the conditions in the early universe. These ancient photons have witnessed the entire history of cosmic evolution from the perspective of light itself, passing through a universe that has expanded, cooled, and structured itself around them. They've traveled through the dark ages when no stars yet existed, through the epoch of first stars and first galaxies, through billions of years of cosmic evolution, and they've arrived at the present day, having crossed the entire observable universe. Yet the photons themselves have not changed except for the stretching of their wavelengths. They carry the same information they always have, a snapshot of the universe, as it was when atoms first formed and space became transparent. In their constancy and their faithful preservation of ancient information across cosmic timescales, These photons embody a kind of historical peace, a resistance to change that allows the past to remain accessible to the present. The uniformity of the microwave background across the sky, varying by only tiny fractions of a degree from one direction to another, speaks to the smooth and peaceful conditions in the early universe before gravity had time to create the dramatic structures we observe today. This radiation comes from a time when the cosmos was a nearly homogeneous sea of matter and energy, when every region was much like every other region, when the universe was simpler and less differentiated. The tiny variations that do exist in the microwave background are the seeds from which all current structure grew. Small density fluctuations that were amplified by gravity over billions of years until they became the galaxies and galaxy clusters we see today. The far future of the universe promises to become one vast realm of cosmic peace as we understand it, though it will be a cold and dark peace, the peace of exhaustion rather than harmony. As stars burn out and are not replaced because the gas needed to form new stars has been consumed or locked up in stellar remnants and planets, as galaxies complete their collisions and mergers and settle into stable configurations, as the expansion of space accelerates and carries distant regions beyond our ability to ever interact with them, the universe will enter an era of profound quiet. This future cosmos will be dominated by stellar remnants like white dwarfs and neutron stars, round dwarfs that never achieved true stellar status, and isolated planets orbiting through the darkness, all slowly cooling toward the temperature of the cosmic background radiation. The brilliant galaxies we see today will fade to black as their stars exhaust their fuel. Their spiral arms will disappear as the patterns dissipate and the organizing forces weaken, and what remains will be collections of dark objects drifting through expanding space, growing ever more isolated as the expansion carries them apart. The universe will enter what cosmologists call the degenerate era, when ordinary matter has decayed or been locked into stable remnants, but has not yet succumbed to the ultimate decay that might occur on even longer timescales. This era will last for trillions of years, a period so long that the entire current age of the universe, from the Big Bang until now, represents merely the briefest opening chapter in a story that will continue for timescales that make billions of years seem insignificant. In this far future, the pace of change will slow to rates that make geological time seem frantic by comparison. A white dwarf will take trillions of years to cool from its initial temperature to something approaching the cosmic background temperature, a process so gradual that measuring any change would require observations spanning billions of years. Black holes, the ultimate gravitational traps from which nothing can escape in the classical sense, will themselves eventually evaporate through Hawking radiation, a quantum mechanical process that allows them to slowly radiate away their mass over periods measured in googolls of years. For the largest black holes, timescales so long that writing them out in standard notation would require more digits than there are atoms in the observable universe. The universe will seem frozen during this era, unchanging over periods that encompass thousands or millions of times its current age, yet existence will continue and time will pass even if nothing marks its passage. It will be a universe in its final stages, having exhausted its capacity for the kind of drama and complexity we see today, settling into an eternal twilight from which there is no dawn. Yet even in this dark future, existence will persist. The universe will continue to be even if there's nothing left to experience or observe it, And in a strange way, the cosmos will have achieved a kind of ultimate peace, the peace of completion, where all possibilities have been explored and exhausted, and all that remains is the slow thermal wind down toward absolute zero. Throughout all of cosmic history, from the Big Bang until the hypothetical heat death of the universe, the peaceful corners have played their essential role. They're the resting places, the spaces between the notes that give the music its structure and meaning, the pauses that make the activity significant. Without these empty, quiet regions, the universe would be a very different place, probably unable to support the kind of stable structures that make complex phenomena like life possible. The peaceful regions provide context for the active ones, making the dramatic events more dramatic by contrast, and offering refuges where delicate processes can unfold without being disrupted by cosmic violence. In contemplating the peaceful corners of the cosmos, we're reminded that peace is not just a human concept or aspiration, but something embedded in the fabric of reality itself. The universe doesn't need our permission or understanding to create vast regions of tranquility. These places have existed long before humans appeared, and will continue long after we're gone, patient and eternal, and utterly indifferent to our existence. Yet somehow their very existence speaks to something within us, the recognition that amid all the chaos and activity of existence, there exist places of perfect rest, where nothing is required and nothing is expected, where being itself is sufficient without the need to become anything else. The peaceful corners of the cosmos are mirrors in which we can see reflected our own deep yearning for tranquility, for stillness, for the kind of peace that needs no justification beyond itself. Thank you for traveling with me. Thank you for trusting me to guide you. Thank you for being open to the peace that's always available, always present, always waiting for you to remember it. Sleep now. Sleep deeply. Sleep peacefully. Let the sounds carry you through the night. Let the cosmos hold you until morning. Let peace be your companion in the dark. You are safe. You are loved. You are home. You are peace itself, resting in the heart of the universe, which is also your own heart. All is well. All is peace. All is one. Good night, beautiful soul. May the stars watch over you. May the cosmos cradle you. May peace be yours now and always. The sounds continue. Your journey continues. But the speaking ends here. What remains is pure experience, pure being, pure peace. Rest now. Sleep. Dream of distant worlds or dream of nothing. Either way, you are held. You are safe. You are loved. The universe is with you, always and forever. Good night.